Okay, so it's really my great pleasure to introduce again Corey Switzer, who used to be here in New York, but now is somewhere in Vienna in Kurt Gödel Research Center, and he will talk about independence in PA, the methods of LN models. Welcome.
Great, great. Thank you, Roman, and thank you all so much for coming. It's so nice to be back here. Hold on, let me just put this into presentation mode. If I do like that, can everyone see okay?
Good. Yeah.
All right, great, awesome. Yeah, so this is really nice. This is my first time back in New York since I left, in a certain sense. But I'm very happy to be here. So what I want to talk about today is a method of proving independence results in PA called the method of LN models. So of course I am kind of assuming that everyone is familiar with the following theorem. So you probably already know what it's going to say. So of course it's due to Gödel, 1931. There are true unprovable statements in arithmetic. Right, and everyone I hope knows, or at least maybe you've, well, I'm sort of assuming you know, otherwise you probably wouldn't be here, that Gödel gave two examples of such sentences. So the first is this sort of self-referential sentence that's kind of like a liar sentence using the provability predicate. And then the second one is con PA. So apparently, and I won't subject you to my diatribe on how I think this makes no sense. You can ask me about it at the end of the talk if you really want to know. But in any case, apparently this is not sufficiently mathematical, whatever that's supposed to mean. So in any case, it became a kind of important open problem in logic. Could you find an example of a true unprovable sentence in arithmetic which was mathematical? And John Barwise at one point referred to this mathematical as saying that it did not require the numerical coding of notions from logic. So this is in the footnote to the Paris-Harrington original paper. He writes this. So, you know, the analogous question, of course, can be asked in set theory, and this was answered affirmatively by Paul Cohen, who invented forcing, and this has become this incredibly successful research program, and it's an important tool in research in set theory and also different areas of logic. I mean, computability theorists use forcing all the time. And of course, it also connects set theory to topology and Banach space theory, all these things. It's a really robust idea. In arithmetic, things didn't totally get off the ground the same way. So the project of finding a non-logical example of independence was achieved by Paris and Harrington in 1977. A funny historical quirk that I discovered when writing this paper is everyone calls this the Paris-Harrington theorem. And for that reason, for some reason, when people put the paper into their bibliography in almost every article, they put Paris's name first, even though H comes before P in the alphabet. So anyway, this was done in 1977. I'm going to talk about their theorem a lot in the second half of the talk, so let me kind of postpone it for now. And since then, there's been an enormous amount of research into both their particular example and sort of mathematical independence and PA more generally, but it's not so robust like in the case of forcing. And a lot of the examples kind of look a lot like Paris-Harrington example, and there's a sort of a lot of the similar kind of ideas that go into them. So all I want to say about the Paris-Harrington example for now is if you don't know what it says, sort of at its core, what it's really saying is that there's a certain computable function f, which is total. And so a priori, this is going to be a pi02 sentence. Because what you're trying to say is that for every x, there is a y, so that f of x equals y. And because f is computable, this last part here is delta 1. And you often hear people say that the kind of, you know, the sort of cartoon explanation for why the Paris-Harrington statement is independent of PA is that this function that they're talking about grows too fast to be provably total. And there's a lot of truth to that. I mean, so Paris and Harrington showed that this growth rate exceeds any PA provably total function. And you know, this is what people sort of attribute a lot of independence in PA is this idea of fast growing functions. And kind of reflecting on this, Harrington and probably, you know, everybody else asked, could there be a true unprovable pi01 mathematical statement? And just note that this is the right question to ask because first of all, there are no true unprovable sigma 01 statements since the standard model is an initial segment of every model of PA. So it's always going to be the case that if a sigma zero sentence is true in the standard model, it's true in every model of PA. But pi 0, 1, we know that you could have a sentence independent of PA that's pi 0, 1 because con PA is, right? You're saying for every x, x is not the proof of a contradiction. So this question of could you have a true unprovable pi 0, 1 sentence was answered affirmatively by Sherlock in 1981. And so Sherlock wrote this really great paper on it. And in the paper, he says this. He says, in the summer of 1980, Friedman and Harrington offered hotly their view that it is one of the main problems of contemporary logic to find a true pi 0, 1 sentence of PA not provable in PA. Now, an answer to such a question is naturally more open to debate than the usual mathematical problem. But Harrington okayed this example that Sherlock gives.
Corey?
Yes.
Can I yell my question? So at this point, just for fairness, how about Matyasiewicz's theorem? And are those statements about solutions of certain Diophantine equations, are they mathematical or not?
I mean, so my opinion is that it's all mathematical. I mean, my opinion is that con PA was a question asked by Hilbert, and if that doesn't count as mathematics, I don't really know what does. But I certainly think that the Matyasiewicz example counts.
Right.
Why?
Right. Yeah, because right, if you look at the date of the paper, it's 1981. So by this time, everyone knew Matyasiewicz's theorem. So anyway. So that just wanted to.
I mean, so I mean, on the one hand, I don't really know that much about the history of this, but like my opinion is that counts. I mean, all of these examples count. So why this one was the one that pulls it over the line as opposed to anything else, I don't really know. Yeah, but in any case, yeah. So I want to talk about this one though. And this paper that Sherlock wrote, I mean, it's an amazing paper. It has just this wealth of ideas. It has a lot more in it than just this one example. He also gives an alternative proof of the Paris-Harrington theorem, which I'm going to talk about in a little bit. And he talks about pi 1, 1 comprehension, and he talks about sort of natural theories of incomparable consistency strength. I mean, all of these different things. But it was, to put it kind of diplomatically, the proofs in the paper are very Spartan. It's not the most easy paper to read. In the same quote here, he says that Harrington was supposed to write up the results and didn't. And I think the implication is kind of like the results were written in a very sketchy way because they had this agreement that fell through. And then it was published in proceedings of some conference and it became difficult to find. And whatever reason, the ideas in the paper were really not digested, I think, by the community. And so the goal of my talk today is to kind of try to systematize a little bit the ideas that Sherlock presents in this paper, and in particular, the ones relating to this true unprovable pi 0, 1 sentence. And what I extracted in the paper that I wrote about this and what I want to tell you about today is a kind of more general method that makes it a little bit more routine to kind of to find these unprovable mathematical sentences, mathematical quotes. Right. So what I want to do with the rest of this talk is I want to introduce the basics of the theory of LN models, which is what this method is, and just develop their theory a little bit. And I actually think that independently, this is a kind of interesting idea that Sherlock had. And then I want to use the theory to first present for you a kind of streamlined approach to Sherlock's, what I think is a very simple alternative proof of the Paris-Harrington theorem. And then I want to just, the one theorem that is sort of much more original is I want to show you a new example of my own of a pi 0, 1 sentence, which is true and not provable in PA, and at least arguably has some mathematical content. I mean, it's not, you know, self-referential or con PA or anything like this. Okay. And maybe I should just say at this point, just to be clear, so my own interest in this stemmed from 2018. I did an independent study with Roman, where I read this paper and tried to sort of mine something out of it, and I ended up writing a paper about it, which is currently on the archive, but I submitted it, and I got back some very nice comments from the referee, and I'm in the process of sort of radically revising it, and so I thought that was sort of as good a time as any to give a talk about it. So what I'm going to talk about today, there's a version on the archive, which you can read, but also hopefully there will be a much better version, real soon now. So before I begin, let me also give a sort of meta-mathematical disclaimer. So the ultimate goal of what I'm going to talk about is I want to be trying to prove independence of certain statements in PA. And so I need to kind of formalize everything going forward within arithmetic. So for the rest of the talk, unless I say otherwise, to be clear, I'm sort of trying to formalize everything in arithmetic. And so every time I say finite, I mean possibly non-standard finite. So I'm never going to sort of step outside the theory and just talk about the real natural numbers or something like this. And then also the anonymous referee suggested something which is very useful. Thank you if you are here. To avoid awkwardness, when I talk about infinite objects, you can formalize that in AC0. And since this is conservative over PA for first order sentences, any argument that I make, if the conclusion is a first order sentence, then you could have argued in PA, right? So that's another way to sort of think about what I'm going to say. Okay, so let's talk about what these LN models are. So like I said before, most of this section is essentially due to Sherlock, but he sort of just took the pieces that he needed as he was making these arguments, and I tried to sort of mine out of it a kind of general theory. So the presentation is a little bit more formal than what you find in his paper, and it's a little more systematized, and I've strengthened a bunch of the lemmas to sort of for this reason. And also, let me just give some more credit that also this idea was discovered independently by Kripke, though it remains unpublished, I think, to the best of my knowledge. And Kripke's idea has appeared in expositions of his work by Putnam and Quincy. Okay, so where are we living? So let's fix a finite signature first order language L extending LPA. For this talk, basically, I'm just going to be thinking of L as LPA, but if you want to throw in a couple extra relational symbols, you can. If you want to throw in some extra function symbols, you can, but then you might need to augment the bounds a little bit in what I'm going to say below, or some constants. If for some reason you really want to have a constant for the number 7 or something, you can. It won't change anything that I'm going to say. So a partial L structure is going to be a set with interpretations for constants, relations, and function symbols from L, defined in the usual way that you always define an L structure, except that the functions can be partial. Okay, that's the only difference. For example, the kind of key example that I'm going to come back to is that if I take a natural number, and again, as always throughout this talk, my natural number can be non-standard, doesn't matter. I'm going to define a structure, it's a natural number n, define a structure m sub n to have universe n, so it's the first n numbers, so from 0 to n minus 1. And then you just define plus and times, etc. as usual, but it's restricted to the set, so they're partial functions. And so if I have a partial L structure, and I have an element in my partial structure and a function symbol f, so that f, as interpreted in M of A is not defined, then, to sort of avoid awkwardness, we're just going to treat this formula as syntactic nonsense. All right, so any sentence that I have with that string, my model M doesn't have any opinions about it, in the same way that it doesn't have opinions about, 3 right parentheses followed by 2 left parentheses. It's just not a useful string of symbols.
Corey, can I ask a quick question?
Please, yes.
Sorry, I didn't mean to interrupt.
No.
Does it matter that you're doing this with partial functions as opposed to relations?
No, I mean, of course, you could do it this way. The utility of partial functions is that eventually I'm going to be building sequences where I want to close off under functions from previous stages, and it's just easier to write down.
Okay, awesome, thanks.
Yeah, but I mean, of course, you could do it this way. And there's actually a paper by Wilkie where he does do it that way, so it's possible. Okay, so M6, for example, it knows that 1 plus 1 equals 2. I mean, I didn't say this, but of course you have this same satisfaction relation. You can define it in the normal way. But if I tried to write down a sentence involving 3 times 4, M6 doesn't know anything about it. It doesn't have an opinion. All right, and so this is exactly to answer Cameron's point. So if I have 2 partial L structures A and B, then I'm going to write that A is a substructure of B if it's a substructure in the normal model theoretic sense that we're used to, but also for each function symbol f in my language, the interpretation of f and b, when I restrict to the tuples of the appropriate arity in A, then it's total. All right. So if I want to extend to a superstructure, I need to close up under function symbols. That's the rule. And this is the thing that's just easier to say this way than as graphs. So this never actually shows up in the theory, but I gave a talk about this at JAF in 2019, and Alf Dolich, who is maybe here, I don't know. Hi, if you're here. He pointed out that an L structure is total, partial L structure is total. I mean, meaning that it's a normal L structure with total functions, just in case it's a substructure of itself. So that's, like I said, it doesn't appear anywhere, but it's worth just remembering. Now, to kind of continue this key example, suppose I had n greater than m squared now, are two numbers. Then my m sub little m is a substructure of m sub n. Because if I take two numbers, k and l less than m, if you add them or multiply them, they're not going to be larger than m squared, which is exactly what it means to say that I close off under function symbols. And if you wanted to add, for example, a symbol for the exponential function in your language, then you of course need exponential here as opposed to squared. Okay.
Sorry.
So now, yes.
Are you sort of starting with like an intended model, or sort of you're fixing a model of PA and then doing all of this within that model, or is this sort of like just because I'm trying to wrap my head around this sort of these non-standard finite the non-standard structures, right? But right, there these relations, the satisfaction relation in two of these might be radically different if you're not fixed within an original model or something like that.
Yeah, so I mean, there's a couple different ways you can do it. In the end, it doesn't affect the truth of the theorems, but yeah, I mean, really you could kind of do it semantically. So you basically do like you say, and this is how I think about it, because I think this is sort of what people do analogously for set theory. You fix a model of PA in your head kind of beforehand, and then you formalize everything there, and that works, and I kind of like that. You could also kind of do it syntactically where, I mean, everything I'm saying, you could kind of write down formally in the language of PA and it would make sense. And you can prove what I'm going to prove, right? And it makes sense to talk about squares and sums and things like that, even for non-standard numbers, right? So you could do it either way. Like, I mean, I like the way that you said, that's how I think about it. But it works as a proof theoretic thing also if you wanted to.
Thanks.
Corey, I have a question.
Yes.
How do you evaluate for all statements with these partial functions? So if I have for all x, f of x has some property, do you only consider things in the domain of f?
Yes.
Okay.
Yes. Yeah.
Okay.
Because if you think about the recursive definition of truth in a structure, to say that for all x blah 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 holds, it means that for each x a certain thing holds. And we need that to be sort of well defined. Well, to be honest, I never really thought about it. You could do it either way. It won't affect, because I'm not actually going to ever talk about truth in these structures, which is what I'm getting to in a second. But I don't think it really. Let's say yes. I think that's fair. That's actually a good point. I hadn't never thought about that. Yeah. Thank you.
Okay. Thanks. Because I was confused about it.
Yeah.
Good.
Yeah. Okay, cool. So the main character of the talk is an Ln model. So what is it? You fix a natural number n, again, can be non-standard. And now an Ln model is just an n-length sequence of partial L structures linearly ordered by this substructure relation. So I start with a partial L structure. Then I close off under function symbols and I get a bigger one. Then I close off under function symbols again and I get a bigger one. And I do this n times. And that's an Ln model. That's it. Okay. Let me pause for 1 second because I know that slides go by fast on an afternoon on Zoom. And this is if you remember nothing else, you should remember this definition. So now just some notation. If I have an ln model, then I'm going to a vector. Then I'm going to denote by a vector to the I comma j as the subsequence where I go from the ith spot to the jth spot. And notice that this is an L of j minus I plus 1 model. Okay. So now my key example continued some more. Suppose I take a sequence of numbers now of length n, so that each one is more than the square of the one before. And I'm just going to call such a sequence of numbers a square increasing sequence for obvious reasons. Then I get an associated ln model, m vector sub little m vector. This should be a calligraphic m, excuse me, where you take those substructures and you place them one after another, and we know that each one is a substructure of the one before because of what I said on the previous slide. So this is my ln model, my sort of favorite ln model, and this is what's called a square increasing model. Okay, and this is really what I'm thinking about. All right, and let me just set a little bit more notation and terminology, sort of moving forward. So if I have an ln model, a vector, I'm always just going to let a sub I be the ith model in my sequence, sort of a standard thing. And in particular, the last model in the sequence I call the top model. And so the point of this whole definition, and this actually gets to sort of Vika's question of why I hadn't thought about some of these formulations of satisfaction, is that we don't really care about satisfaction in the partial L structures. Instead, there's a kind of new satisfaction that we define on these sequences, which is called fulfillment, and can be used to code consistency statements into finite combinatorial ones. To give you this definition, I need just a little bit of syntax. So if I have a formula phi, I'm going to denote by dp of phi, the depth of phi, just the number of quantifiers appearing in phi. Not the number of quantifier alternations, the number of exists or for alls that appear when I write down phi. And I'm also going to write sort of, cardinality phi like this as the syntactic length. So the number of symbols, period. Now here's my definition of fulfillment. So this is our sort of satisfaction relation for these sequences of models. Okay, so there's this whole piece here about the parameters. It's kind of sticky and technical. I think instead of reading you through this piece here, which doesn't make sense until you've seen an example, which I'm going to give, what I want to say is, for the moment, just pretend that all of the parameters and all of the terms that you would need to deal with for some formula phi, suppose that all of that lives in the first model in some ln sequence. Okay, so everything is in the first model. And what I really want is that I want everything to be sort of well-defined, very far below the top model. So I don't have to go sort of all the way up to the top of the sequence to know what's going on. This is what this says, essentially. So for the moment, just pretend that everything makes sense in the first model, and we're going to define this notion of fulfillment from there. So I have a formula phi, and I have this ln model A, and I want to tell you what it means to say that A fulfills phi. So first of all, if phi is atomic, then A fulfills phi just in case the top model thinks that. All right, and note this is an atomic sentence, so I don't have to worry about this universal quantifier. All right, for the Booleans, it's exactly what you think it should be. So if phi is of C1 and of C2, then A fulfills phi just in case it fulfills each of the conjuncts. And the same for the disjuncts. And for negation, A fulfills phi of A vector just in case it's not the case that it fulfills the negation. The interesting case is the quantifiers. This part here is exactly the same as in the previous definition. I just left it up so you could read it. If phi is a sentence of the form, there exists, a formula of the form, there exists a y such that of c of y comma x vector, then A fulfills phi of A vector, just in case I can find a B, and here it says AI plus 1, but what I mean is that the B has to not just come from one of these models, it has to come from the next model after the one where I got all my parameters and defined everything. So I can't go arbitrarily high up in the LN model to find my witness B. It has to come from the next one. Okay, so I pick the next one, and then I forget about this whole section that I had before, and I just look at this end segment of my sequence, and I say, does that fulfill if C of B comma A vector? If this appears strange to you, I agree. It's not natural to me, but it turns out to be exactly what works, and as you start to work with it, you sort of see why. And then for the universal case, what I need to know is that if I take if I have phi as for all y of C of y comma x vector, and A fulfills phi just in case, if I look at any j which is after I, but sort of low enough down, so it's below n minus the depth of C. Then if I look at every element in one of those more bottom models, we get that A fulfills this. So in both of these cases, what sort of goes on is that if I strip off a quantifier, I'm allowed to go up a model. And so we always want to make sure that we're sort of low enough down below n that I can always strip off a quantifier without finding myself up too high that I get stuck in this problem that Vika asked a question about.
Corey, can I ask you a quick question?
Please, yes.
Okay. Since you had defined also recursively what it means to be fulfilling a negation, this second bullet item involving the universal quantifier is not really necessary. You're just basically pointing out the ramifications of the existential one with your negation clause.
Yes, I think that's true. I think that's true. It's a little bit weird when the depth of phi and n are too close together, things get weird. But it definitely, as long as n is sort of big enough, then that's definitely the case.
Thank you.
Yeah, yeah.
Right, so, sorry,
Yes.
to follow up on that. So the point is though, but if n is not large enough, then it might not be that for all x, phi x is not exists, not phi x.
Yeah, there seems to be cases where you cannot reduce to the previous, especially because the existential seems to be so specific to the next level.
Right, that's right.
And also one thing that might be related, and in the existential definition, you have to chop off the n model to a shorter model. There you have the interval I plus 1 to n minus 1. So that's like n minus I or plus 1 minus 1, I don't know. Whereas in the universal, in the end, you have the full ln model. You don't chop it off, or should you? Because that's, that might make quite a difference at some point. When for the existential, you're really dealing with a different ln model, a shorter ln model, and that's where you go to look for the witness. Whereas for the universal, it's the whole thing again.
Yeah.
Does that make any? Is that an important point, or?
To be totally frank with you, so I thought this was an important point, and that's how it is in Shellow's paper, and early on in the draft of my paper it was like that too, and I realized I never used that, so I got rid of it because I thought less symbols is better. We're gonna see that this fulfillment, you'll say, well, I'm gonna prove a theorem about fulfillment that it is on the next slide, so let me not just say it when I can show it to you. But it says that basically this kind of awkwardness you're talking about, it can happen for small n, but for what we're going to do, we actually want to look at what happens as n gets large. And after a couple steps, it kind of goes away. The awkwardness that can happen is that because this is so tied to the syntax, equivalent statements, it might be the case that one of them makes sense to talk about for a short n, and one of them no longer makes sense. And this is actually kind of the weirder thing than that you could have a case where you're fulfilling two sentences that are contradictory, which I don't think can happen, but it certainly seems like it's not totally clear. Yeah.
Correct. Could you please give an example? Or maybe will you present an example of when fulfillment of a sentence is different than, let's say, something something simple about satisfaction in the models in the sequence, right? So that it's really, you know, so that really see that something.
To be honest, I can't give an example because I don't really know if there is one other than this thing that could happen, which is that the sentence is too long to be fulfilled by a short model. I'm gonna get there in a second, but the theorem is that a sentence is tautological. It's provable in whatever your favorite proof system is, just in case it's fulfilled by every ln model for sufficiently large n. So once n is kind of big enough, it's going to be fulfilled by that model, just in case it's, there's going to be a model which fulfills it just in case it's consistent. So it kind of stabilizes, if you like. But the point is that it does it in sort of slow pieces, which is what's going to be useful in proving these statements. What I think will be helpful and hopefully will help you is I have a worked example of a very simple sentence that is also going to be a useful lemma later. So recall that Robinson's theory Q is the following set of sentences. All right, so I'm not going to read them all out to you. It's exactly what you think it is. It's PA minus induction, or it's one way to axiommatize PA minus induction. So for example, the first one says that 0 is not the successor of anybody, and the second one says that the successor function is injective, and the third one says that everyone other than 0 is the successor of someone, and so on and so forth. And the thing that'll be important on the next slide is that every single one of these sentences has either one quantifier or two quantifiers. If I wanted to be really careful, I probably should have put a for all for each one, but I didn't. So the proposition is that if I have a square increasing model of length 3, why 3? Because I needed to be bigger than 2. But because the depth of each one of those sentences was 2. And I take a square increasing model, then we have that m sub n, this square increasing model is a model of Q. And what I mean by fulfilling a whole set of sentences, I mean it fulfills each one. And it also, and actually, sorry, this maybe answers the point. I'm sorry, I can't see who's talking, so I don't know who asked that last question, but this maybe answers your point. It also fulfills that the less than order, the natural PA order, is a linear order with no greatest element. And that's actually different than satisfaction, right? Because this is a finite sequence of finite models with a finite linear order on it, but it thinks that it's infinite. So there you go. So it can be wrong, but it'll be wrong for a reason that's kind of instructive. Right, so the surprising of these is the last one. This is what I said. So what I want to do is I want to show you why, I'm not going to go through every single axiom, but I want to show you why it fulfills the first axiom and go through it in some detail. And then I want to show you why it thinks that the linear order has no greatest element. Right. So the first axiom, remember, this is the one that said that 0 is not the successor of anybody. For all x, 0 not equal s of x. All right, that's the sentence, the syntactic form. And I have my square increasing sequence of numbers and my associated square increasing ln model. And for simplicity, just to kind of make things work a little nicer today, let's just assume that the first element is greater than 1. Okay. So this statement has parameter 0, and it has this term s of x. And so if I apply 0 to s of x, I get 1. So there's sort of two numbers here that kind of maybe could appear somewhere in this 0 and 1. And the point is that because we assumed m0 was greater than 1, they all live in the first model, which is kind of just makes things a little bit nicer to talk about. All right. Otherwise, we could go to m1 and we could work there. And yeah. Now, moreover, this sentence has depth 1. It has one quantifier. So n minus the depth of this axiom minus 1 is n minus 2. Okay. Now, per the definition of fulfillment, what we need to show is that for each j in between 0, where where all my parameters live, and n minus 2. So that was the depth, this n minus the depth of the axiom minus 1, and each a in m sub little mj, that m sub little n minus 1, because this is a atomic sentence now. So we remember the fulfillment for atomic sentences meant that it's true in the top model. So that for each a in this one, the top model thinks 0 is not the successor of a. That's obviously true if the top model defines the successor of a, right? If this makes sense. But it does make sense because we picked A not from the top model, right? It came from at most n-2, so the one before, which means that it's defined, and so it's true, right? Because mn-1 contains not only every element from m sub n-2, but also up to its square. So I mean, it's overkill, right? You need to get to the square for some of the other axioms. Was this helpful? I mean, do people have any more questions about this before I move on to the other example?
I think that's good.
Good. And so it's sort of not so hard to see why this this sequence fulfills that less than is a linear order with no greatest element. Sorry, is a linear order. Excuse me. The interesting part is why it has no greatest element. And so let's do that one also in a little detail. So it's not hard to see that the less than is linear. What's surprising is that even though the structures are finite, they have a greatest element externally. It's not fulfilled by the sequence models. So to see this, what does it mean to say it has no greatest element? It means that for every x, there's a y which is greater than x. That has step 2. So notice that we have n-2 minus 1 is n-3. So this square increasing model fulfills that sentence just in case for each j in between 0 and n-3, in every b and mj, let's just say m sub mj, we think that there is a y so that b is less than y. But now the point is that I picked my b from at most the n-3rd model. And so what I can do is I need to be able to then go to the j plus first model. So at most the n-2nd model and find something larger than b. And clearly I can do this, right? The whole point is that this whole situation is set up so that I can only talk about stuff that comes from sort of early enough along in my sequence of models. And the way that I like to think about this is that what we're doing really is we're trying to build an infinite model in finite stages. And it's only after we've sort of gone out really far that we're able to look back and sort of look at what we did, right? And so the fact that this linear order is going to be, has no greatest element, what that's really saying is, well, I'm just going to keep building. So I know that no matter, if I keep building them, then I'm not going to have a greatest element because any element I put, I can build past it. That's what I view this as saying. Okay. Okay. So as I mentioned, when people were asking questions before, this fulfillment has a kind of completeness theorem. So just as some terminology, let's say that a sentence phi has a model if there's a total L structure so that M models phi in the normal sense. And it has an Ln model if there is an Ln model which fulfills it. And again, we can choose to formalize phi has a model in ACA 0 just to make life a little easier. So you can prove this result. It's sort of similar to how you prove finite Ramsey's theorem from infinite Ramsey's theorem. I'm not going to do it just because of time constraints. You could also prove it using a proof system if you want to formalize that, and that is also not so hard to prove. But so if you have an L sentence phi, then phi has a model if and only if it has an Ln model for all n greater than the depth of phi. All right. So this kind of says that it's consistent just in case no matter how far out I build, I can find something that fulfills it. And if I fix the proof system and I apply the conservativity of AC 0 over PA alongside the arithmetized completeness theorem, then we get the following: that if I have an L sentence phi, then phi is not provable from the empty set, just in case for all sufficiently large n, and there's an Ln model of not phi. And it is provable from the empty set if every Ln model fulfills phi for sufficiently large n. Okay. And this is kind of what I was getting at. With a lot of these sort of indices, they don't matter in the long run because once n is sort of large enough, you know what can and can't happen. Okay. So we get as a consequence of this a sort of completeness theorem for satisfaction, for fulfillment. So an L sentence phi is provable just in case for all n greater than the depth of phi, all Ln models fulfill phi. And the way we're going to use this to prove independence in PA is use the following corollary. Note that this completeness theorem was proved in PA. So the statement that for all finite subsets gamma of PA and all n greater than the max of the depth of gamma plus 1 for little gamma and gamma has an Ln model is equivalent to con PA. Right.
Corey, can I ask a question?
Please,
Maybe this is just my confusion, but these Ln models, I thought these were very like arithmetically based. So they're supposed to, in particular, like, you know, they need these arithmetic operations and this order things. You can say less than the square, etc.
Oh, I see what you're saying. No, they don't have to be. I mean, I guess, what am I saying? So I did say at the beginning that we think of L as a model in the language of PA.
Oh, but it's a general definition then.
Right, it is. And also,
okay.
I mean, nothing was making it that you had to interpret the symbols, you know, in agreement with what, you know, what was going on in PA or something like that.
All right, great. That clears up my confusion. Thank you.
No, that's a good question. Yeah, sorry, I should have said that. Right. I mean, these are just general structures in the language.
Corey, so a bad question now, because I'm always confused at this point that when you say for all finite subset of PA gamma, so gamma is really finite and PA. No, I see.
No, because I mean, that's just true. I mean, right, without the quotes here, as you know, this is just a true sentence, right? Because PA is consistent. I mean, maybe it's not, but then what are we all doing here? What I'm saying is that PA proves.
This is the arithmetized sentence.
Correct.
Okay.
Right. Exactly. So I mean, by PA, I mean the delta 1 sequence, definable delta 1 sequence of axioms, and yeah, exactly. Right. And this max here, you have to interpret it in PA. So this might be a non-standard number, and these might be non-standard length sentences. Yeah, one needs to be careful about that. Right. This is why this whole thing will work, because I want to prove. Ultimately, I'm going to prove con PA from PA plus a combinatorial statement. And I need to show that combinatorial statement proves this part here. Okay. Yeah, so that was good to know. And then one more application one more lemma about LN models. I know I've spent a lot of time setting up the scene, but this is the last sort of basic background lemma that I need. And this one is kind of the most magic of them all. This is called the finite model lemma. So it's a kind of, this is too much text, I think, on a slide, but it's a kind of Löwenheim-Skolem theorem for LN models. And what it's going to say, essentially, is that if I have a sentence sigma, and I have an LN model A vector which fulfills sigma, then I can find a new LN model B, which also fulfills sigma, and the cardinality of B is going to be sort of small. In fact, it's going to be computable from I and sigma and a couple other parameters, but it's not going to depend on A. I mean, my B will be a substructure in a certain sense. So that'll come from A. But the size of the LN model that I need to in order to know whether or not I fulfill sigma is going to be sort of small and not depend on A. All right. And so in order to make sense of this, because we're arguing in PA, we're just going to assume that there's a sort of, if I have an LN model A vector, it has an external well order. And that's what we're going to be using. We might sort of talk about the least element such that blah, blah, blah. And it doesn't really matter which one you chose, but that's how we're doing it. So the finite model lemmas is the following. Suppose you have a natural number n, and phi is an L sentence of depth at most n minus 2. Okay, so I have the cardinality of the signature of L, and J is the least size linearity of a function symbol. Now suppose I have an Ln model A vector, and there's another Ln model B, then the lemma says that there's another Ln model B with the following properties. So B0 has cardinality at most the signature of L, excuse me. And Bi plus 1 has cardinality at most this disgusting recursive formula, which I'm not going to read to you. But if you glance at it, I hope it's clear that if you really wanted to punish yourself, you could compute it. But note that it depends on what the cardinality of the previous one was. It doesn't depend on cardinality of anything in A. And it's also primitive recursive. That's the other thing that's important here. I mean, I'm taking, sums, and I choose m's and exponents. And the universe of each BI is a subset of the universe of AI. Not necessarily a substructure in the sense I defined at the beginning of the talk, but it's a subset. So I'm taking elements from AI. And finally, the sort of important point is that for each subformula of C of phi, B vector fulfills of C if and only if A vector fulfills of C. So I get a kind of elementarity with respect to subformulas of phi, and in phi in particular. Okay. And moreover, the way that we construct this B is such that if I know about phi and I know about L and I know about A, then I can compute B. Okay, and so these bounds are emphatically not best possible, especially so because in the actual proof in the paper, which I'm only just going to sketch here, for some other applications I'm not going to talk about right now, I add in some extra bells and whistles, which means I have to add in a couple more things, and then that changes the bounds. So, but in any case, I was very lazy with them because it doesn't really matter. What matters is that the bounds are going to be recursive in the index I, the length of phi, the size of L, sorry, this is a typo. This shouldn't say, there is no M, excuse me. And J, which is the least size, the greatest size of an arity, greatest arity of a function symbol in L. Remember, L was finite, so there is a greatest one. And so in particular, it doesn't depend on N or A. So I'm going to denote this bound, this primitive recursive function by call of IJKL. It's the collapse, it stands for collapse, because I think of this as a sort of collapse of this bigger structure A. So the lemma states that the size of BI is at most call IJ phi L. How does it go? Well, so you define BI by induction, and it's clear sort of that what you're doing is recursive in what we're talking about. So for B0, you just take the individual constants plus some extra element if you don't have any constants. So just the smallest number of things that you need to even have a structure. And then if you have BI defined, first thing you do is you close up under function symbols. Then the next thing you do is for each subformula of phi of the form there exists a y such that of C of y, comma x bar, and each a bar that was in my BI already constructed, if a vector thinks that there exists a y such that of C of y, comma a bar, pick the least b and ai plus 1 witnessing this and throw that in. And for universal statements, if a vector thinks that the negation of the universal statement holds, then pick a witness there as well. And there's a kind of Tarski-Vaught argument that you just needed to pick out enough witnesses in order to make this sort of pseudo-elementarity work. And so my BI plus 1 is just my old BI when I closed under the functions and then I added all my B's and C's that I needed. And if you go back and count and you're very lazy about counting, as I always am, you'll get that disgusting formula that I showed you 2 slides ago. Okay, so that's how it works. It's not so hard, but I think it's kind of surprising. And then the point is that using this finite model lemma, if phi has an ln model A vector, which is linearly ordered, I guess I don't need that it's linearly ordered. I'm sorry, this is a typo as well, excuse me. If he has an ln model A vector, then by this finite model lemma, it has one that, you know, is kind of small. I mean, it has size at most collapse n minus 1, comma phi, comma k, comma L. I don't know why this extra n is here. And so what I can do is I can kind of isomorphically send that structure, that sequence of structures, onto just the first call of n minus 1, comma phi, comma k, comma L elements. All right, so I can just assume that the universe of the whole sequence lives on just some initial segment of natural numbers that I computed primitive recursively from the parameters I was interested in. And so I'm going to call such a structure the F collapse of A for phi. So F for fulfillment. So I think of this as a kind of Levenheim-Skolem collapse, or a Mostovsky collapse, where you have some big H kappa, and then you collapse everything down to some little real that was what you actually cared about. It's the same kind of idea. And what the F collapse is going to give us, what we'll see, is that it's going to allow us to bound that universal quantifier in the pi02 sentence to get a pi011. All right, but more on that later. All right, so I'm going to turn to some applications now. Before I do, are there any more questions about LM model? Cool. So let's see some applications. So I want to present to you a proof of the Paris-Harrington theorem that uses this technology. So I hope that'll sort of be sufficiently, well known to people that it makes it clear what's going on, and then it also sort of exposits the theory. And then the second application will be a new Pi01 one. So the Paris-Harrington principle, pH, recall this is the following statement, that for every ek and r, natural numbers, there is an n, so that if I color the E size subsets of n in r colors, then I can find an H which is homogeneous for this partition, meaning that H, the E size subset of H, when I apply the partition to them, it's constant. This H has size at least k, and then the important point, because so far I've just told you finite Ramsey's theorem, and the cardinality of H is larger than the minimal element. That's what makes this Paris-Harrington and not Ramsey's theorem. All right, and it's very surprising and beautiful that this one is independent of PA, but Ramsey's theorem is not. I mean, this is one of the great things, I think, in logic. Right, so this last part is what separates pH from finite Ramsey's theorem. So the Paris-Harrington theorem is the statement that pH is independent of PA. How am I doing on time? I've been speaking for a little under an hour. I have like half hour left or something like this.
Well, just I think you're fine.
Okay, so let me just very quickly remind you why pH is true in the standard model. All right, so the Paris-Harrington principle is true in the standard model. It goes like this. Well, suppose not. And you fix ek and r, so the principle fails. All right, so that means that no matter how big an n I choose, I can always find a partition on the E size subsets of n in r colors with no homogeneous subset of the kind that Paris-Harrington says exists. And so let me take the collection of all such partitions like this. Okay. And now this subset T, it's an infinite tree. It's an infinite set, right? Because there is one for each n. And moreover, I can order this T as sort of the tree ordering by saying that if the P will be below Q in this ordering, just in case P is a partition on n, Q is a partition on some larger n prime, and when I just look at what Q does on n, I get P. All right, so it's an extension relation. And you can check that this is a tree ordering and that you get a finitely branching infinite tree. And we all know what happens when you have a finitely branching infinite tree. You apply Koenig's lemma, you get a branch. And now I take the union of the branch, and that's a function from the E size subsets of the natural numbers into R. It's a partition of E size subsets of omega. So infinite Ramsey's theorem tells me that I get an infinite subset of omega on which my partition is constant. And now I get a contradiction, because I have an infinite set. So all I have to do is find a large enough n so that that infinite set below n has size larger than k and size larger than its minimal element. And that's not hard to arrange. But then if I look at my partition restricted to that set, that gives me the homogeneous set on this big enough n that I thought wasn't there. So that's my contradiction. Okay. Now let's work towards proving the interesting part of Paris-Harrington, which is that it is not provable in PA. So this was proved in 77 by Paris and Harrington. So pH implies con PA is what they showed, and so in particular it's not provable in PA. So pH is independent of PA. So how are we going to show this? Well, so let's define a theory PF stands for parameter free sub k. What is this theory? Well, I take the axioms of Q, and then I take the first k instances of the parameter-free least number principle relative to my favorite ordering of the formulas of PA, computable ordering of the formulas of PA. So the least number principle just says that if there is an x as the P of x, then there's a least one. And it's known that if I take the union of these theories, I get PA. Okay? So the goal is to show that PA plus pH implies con PA. And in light of this special case of the completeness theorem for Ln models, what I need to show you is that if I assume pH, then I get that for each k, and all sufficiently large n, there is an Ln model of PA PFK. All right, this proves the theorem. Okay. So before beginning on this proof, let me just isolate a slightly modified version of pH, which is what I'm actually going to use in my proof. And this slightly modified version, it follows from a more general statement, which is also equivalent to pH, that was shown by Paris and Harrington in their original paper over the base theory PA. Both their general statement and this special case that I need are ostensibly stronger than pH, but it turns out that they're equivalent over PA. There's something interesting going on here that you would have to look, I think, at weak arithmetic in order to understand that both in this proof and in Paris-Harrington's original proof, you seem to need this sort of ostensibly stronger case of pH in order to get consistency of PA. But since PA proves that they're equivalent, you know, whatever distinction there was there gets erased. Anyway, so some more notation, n bracket e sub square increase is the set of e size subsets of n, so that if I place them in ascending order, they're going to be square increasing. And so pH implies that for each ek, r, and m, I can find a large enough n so that every function f from n to the e sub square increase into r, I can find a homogeneous h, which is square increasing. So f restricted to just all the e side subsets of h makes sense. H contains only elements larger than m, and so that the cardinality of h is larger than the minimum of h plus k. So we have that min h is greater than m, and min h plus k is smaller than the cardinality of h. So it's a sort of stronger square increasing version of Paris-Harrington. All right. Now let's prove the Paris-Harrington version. All right. So remember what we're trying to do is we're trying to show that PA plus pH implies that for each k and all sufficiently large n, I can find an Ln model of PA, the parameter-free PA k. And we know that every square increasing model of length at least 3 is going to fulfill Robinson's Q. So what I need to show is that I can find square increasing models of every sufficiently large n modeling any finite set of sentences in PA. So for simplicity, let me just fix a sentence phi. And I just want to show you how to find, for any sufficiently large n, a square increasing model satisfying the least number principle for phi. All right. And then you have to just sort of up this to finitely many parameters. And it hopefully will be clear enough in the argument that this is not too much of an overstretch. So fix n that's at least size depth of phi plus 3. I don't know if you totally need 3. I think you need 2 actually, but I like to give myself an extra number because I'm always worried. And now, if I can find a square increasing Ln model that fulfills, it's not the case that there exists an x such that phi of x, then we're already done because you've trivially satisfied the least number principle for phi. So suppose that all square increasing models of length at least n fulfill that there exists an x such that phi of x. So what we need to show is that they all fulfill that, or at least one of them fulfills that there is at least such x. All right. And let's also fix a number m, which is large enough that all the terms in phi that we're going to need are definable in m. So this is akin to kind of just saying, we want to make sure that in my first model of my Ln model, everything I care about is already well defined and whatever. All right, now having set the scene, let's prove the theorem. So if I take any square increasing sequence, so that the first element is greater than this m squared, I can define a function f sub phi of m vector to be the least x, so that m vector sub little m vector fulfills phi of x. And this function is defined on all square increasing sequences of length m plus 1, whose first element is larger than m squared, by my assumption that every Ln model like this thinks that there is a witness to phi. And now my coloring is going to be on n tuples, f prime of phi, and we're going to color an n tuple, a square increasing n tuple above little m. We're going to color it 0 if, when I swap out the m1 for m2, I fix m0, but I swap out m1 or m2, I get the same least x. and I'm going to color it 1 otherwise. All right. And that's a 2 coloring on these n tuples, square increasing n tuples. Now I have pH, so I apply pH. So I find some large enough n so that when I restrict my coloring to that n, I get a nice homogeneous subset. Every element is larger than m squared. And my cardinality needs to be at least the minimum of h plus n plus 5. You'll see where 5 comes out in a second. But this is what Paris-Harrington, or this lemma that I gave you about Paris-Harrington, tells me that I'm allowed to do. And the claim is that my coloring restricted to this homogeneous set is 0, so not 1. Why is that? Well, otherwise it would be 1. And what that means is that if I have my square increasing sequence and I fix my 0 and I just walk up, so I do m0, then ml, then mk minus n minus 2 up to nk, and I let my L go from 1 to k minus n minus 3. So I just shift around my indices because I have a lot of room to play. That's going to be a subset of m0, right? Because each one of these FVs picks out an element less than m0. And because I'm coloring everything with 1, that means that each one of these, when I change my L, I'm going to get a different element. So it's an injection from, basically from this sequence from 1 to k minus n minus 3 into m0. And so how big is it? Well, it has to have size k minus n minus 4. All right. But what we assumed is that k was larger than m0 plus n plus 5. That's a contradiction, right? Because on the one hand, what this tells me here is that m0 is greater than or equal to k minus n minus 4. And this one says that k minus n minus 5 is greater than m0. So my coloring is identically 0. And because my coloring is identically 0, I'm going to claim now that if I take just the first m elements in my sequence, that this associated square increasing model thinks that x0, which is what I'm calling that same least element that all of these things think is the least witness, that m0 thinks that's the minimal x, so that phi of x holds. That this witnesses my least number principle in my LN model. Well, otherwise, it would have to think that there was a y less than x0 so that phi of y holds, right, if it's not the least. So that means that by the definition of fulfillment, there's a corresponding y less than m1 so that m vector from 1 to n thinks phi of y and y is less than x0. If it thinks that y is less than x0, y is actually less than x0. Because it's agreeing with the PA order. That's how I constructed the model. And it thinks that phi of y holds. But that's a contradiction because my coloring, this homogeneous set, was such that any n tuple, including this one, had to think that the least such x satisfying phi, fulfilling phi, was going to be x0. So that can't happen. So m sub n vector here thinks that x0 is least. And just to conclude, putting that all together, if I make my bigger LN model where I put my first parameter set at the beginning, m sub m vector, then the whole thing is a model of the least number, fulfills the least number principle for phi, which is what we needed to show. So we're done. All right. And like I said, to up this from one formula to finitely many, it's the same argument. You just need to keep track of more indices. So that's the proof that Paris-Harrington implies conp from LN models. Now, I want to do this again, but I want to do it for a pi01 sentence. How are we going to do that? So the idea is that we need to remove this, unbounded existential quantifier in pH, the one that was the exists of big enough n so that you can do whatever. And so what I need is I need to restrict my sentence to some class of partitions P whose behavior is already determined by some small subset S, whose size I can control in a bounded way. However, at the same time, the class of partitions needs to be rich enough that I could still run a version of the argument that I just gave you. So how do we do this? Well, we have this collection of structures now. I like them. We've been thinking about them. Let's try coloring the LN models as opposed to just arbitrary sets, and then try to apply the finite model lemma in this set. All right, so this is the idea. So how do we do it? Well, let's fix natural numbers R and capital N, and take a phi of x, an L formula phi of x, one free variable. So a bounded, what I called here, I don't totally love this terminology, to be honest. So if anyone wants to say they hate it and suggest a better one, please feel free. A bounded n phi coloring in R colors on n is a function f so that the following conditions hold. So my domain of f is going to be exactly the set of Ln models A vector, so that the top model has its universe contained in this large n. Right, so everything is kind of coded into a subset of n. And it fulfills phi of b for some b in my in the sequence. All right, so it's kind of, you can think of it as kind of like an Ln model version of an elementary class, right? So if phi says that it's a group, then you look at all of the groups, all of this Ln sequences of groups, bounded by some size. If phi says that it satisfies a certain theory of arithmetic, same thing, right? Some sort of axiomatizable, whatever that means in the context of fulfillment, collection of models, sequences of models.
Corey, can I?
Yes.
Because I see that you have 11 slides left, but we
Yes.
don't have that much time to go through all of those slides. So maybe you can just make sure that we understand what the statement of the theorem is, but perhaps we'll have to skip the proof.
Okay, that's totally fine. Yeah, I can. Do I have like 10 minutes? Is that okay?
Well, I'll stay here, but I see that some people are already leaving. So.
Okay. Oh, sorry about that. Yeah. Sorry.
No. Well, they are leaving. I'm not.
All right. Yeah, I'll be quick. So yeah. All right. So anyway, let me say it faster. I'm coloring.
No, don't say anything faster. Just take your time.
All right. I'm coloring Ln models, that are sort of axiomatized, if you like, by some fulfillment phi in R colors, and with this additional boundedness requirement. It says that for each k greater than n, if I take some long sequence, longer than n, some LK model, and I look at the F collapse, this finite model collapse that I told you about, so I collapse it down to some tiny little substructure, and I look at any n tuple of indices, then how I chose to color the small n tuples, the little collapsed version, was the same as how I chose to color the big one. So all I really need to know in order to know how F behaves is what it does on the F collapses. And this is going to be how I bound my existential quantifier. Right, so because everything is bounded by this big N, we say that F is bounded, is a bounded n phi color and n colors on n is delta 0 with these parameters, because everything I said was bounded. So my true pi 0, 1 sentence is the following. It's kind of annoying. I have a lot of parameters. You have to quantify over a lot of things, but so be it. So it's BCP, the bounded coloring principle, says that for all R, N, L, V, J, M, and K, if I have an N phi bounded coloring in R colors on this bound that I get from the Ln model lemma, this primitive recursive bound, applying my parameters here, then I can find a homogeneous sequence of structures of some length k bar, at least k, so that F is homogeneous on any n tuple of these structures, and the length of the sequence is more than A0 plus any extra little bit that I need. All right, so it's similar to Paris-Harrington, except that instead of the existential quantifier, I have this primitive recursive bound that I basically tailored the definition of boundedness for. All right, so just note that what this says is that for all, and in this long sequence of parameters, a certain, every coloring, every coloring has a certain property and everything is bounded by this primitive recursive bound. So it's pi 0, 1. And so the theorem, which I think I'll just sort of skip through the proof more or less, is that BCP is true in the standard model, but PA plus BCP implies con PA. So in particular, it's independent of PA. And let me just kind of tell you what the idea behind the proof is, and then I guess I'll leave it there. So BCP is equivalent to the statement where instead of putting that primitive recursive bound, you just say there exists some n so that the whole thing works out. The pi 0, 2 version. All right, and this is what boundedness is tailored for. So why is it true? Well, suppose that you just knew that there was some large enough n to witness the claim. So so I need to show you that actually your homogeneous sequence of structures is all living on some small collapse set already. But if I have a some big homogeneous set of structures, I can apply the F collapse to them. And that gives me my small homogeneous set of structures. And I know that my coloring has to behave the way I need it to on the small set because of the way I define boundedness. And that's the point. So now the point is that my pi 0, 1 sentence that I gave you is equivalent to this pi 0, 2, 1 that now looks like a structural version of Paris-Harrington. And the structural version of Paris-Harrington then is true and unprovable essentially by the same argument that I gave you for Paris-Harrington. So I was going to go into it in detail, but maybe I won't. But the point is just that we can show that for each phi and any sufficiently large n, there's an Ln model of the conjunction of all of the Q axioms and the least number principle for phi. And that's what this says. So this is the proof. And then I'll skip through this, but it's the very, very similar argument. And let me just kind of finish by saying, so using this kind of framework, one can actually prove a lot of these sentences. It starts to feel a little routine. So for example, I can show that given an alternative proof of Kanamori and McAloon's regressive Ramsey theorem, which is an example they gave that's related to Paris-Harrington. And I can even give a sort of similar modification to a pi 0, 1 Ln model version. And also it seems like you could do sort of similar pi 0, 1 examples like this. So thank you for your attention. And this is Sherlock's paper, and then there's mine. Those are my references. So thank you so much.
All right, thank you, Corey, very much. It's becoming clearer and clearer, although there is still probably some way to go. But anyway, it's open now for questions.
I would like to ask another question since I haven't asked enough. So these Ln models are finite in length, the sequence.
Yes. Mm-hmm.
And so, this like completeness theorem, or not completeness, the fulfillment theorem was like, for arbitrarily large, for large enough n, why not just make them infinite in length? And then it would seem if they're infinite in length, everything is long enough and you could just say it directly. Is there an advantage to restricting to finite length versus allowing length omega in the sense of the model?
So, I mean, I'm trying to formulate everything in terms of PA, and I'm ultimately trying to formulate finitary Ramsey theoretic statements. And that's why you do it like this. If you just let the model,
well, because you're doing it in ACA not though, so you could do that and then maybe cut off to a finite piece as necessary for this Paris-Harrington thing. I don't fully understand the proof of the Paris-Harrington part, so maybe there's something there that I'm missing.
No, I mean, so if you go, well, I'm not going to try to go all the way back, but the theorem I had in ACA not that there is an Ln model for all sufficiently long n, just in case there is a model in the normal sense, is basically what you're saying. So the way that you prove that is that if you have an Ln model for all sufficiently large n, you build a tree of attempts to extend it. And then because ACA 0 is enough to prove Koenig's lemma, you get a branch, which is your model.
Right, okay.
So you can kind of, there is this correspondence, and that's actually what the ACA 0 proof gives you.
All right, thank you.
I have I'm sorry, Ken, go ahead.
Oh yeah, I am. Example, in Pripke's paper, recent paper about the pi 0, 2 independent statements, he refers to Gödel's first presentation of his incompleteness theorem, a meeting somewhere in Germany, a meeting at which von Neumann was present. And apparently Gödel's first unprovable formula was a combinatorial statement.
Oh, that's very interesting. I didn't know that.
Yeah, and it's only von Neumann who urged him to turn it into a number theoretic statement, which he, of course, did brilliantly. Also, apparently, von Neumann wrote him a letter a couple of weeks later or a month later saying, by the way, your statement implies the consistency of Peano arithmetic. And Gödel answered, oh, yes, I just realized that.
Oh, that's very cool. I didn't know that. That's fascinating.
Yeah, so these are two facts, but I'm just wondering if anybody knows enough about the content of that original combinatorial statement that Gödel put together and how it would compare perhaps with your analysis, because it would be a pi01 statement. So it's
Yeah, that's a good question. I have no idea. I didn't know that. This is news to me. This is very interesting. I don't know. That's. I'm sure that if those letters are found, I mean, I'm sure that they're in some library somewhere or something. But that would be interesting to know. Yeah.
Yeah, Kripke might be a person who knows what's going on here.
Yeah, I don't know that much about Kripke's. I mean, I mentioned Kripke did this sort of similar analysis. It's mentioned, like I said, by other people, but I don't actually know anything about his work on it. I haven't been able to find anything.
He refers to this combinatorial statement in a footnote in his recent paper.
Oh,
That's why I mentioned Kripke. That's why I mentioned Kripke.
Yeah, or I'll look at that. I haven't seen that. Thank you.
Let us know what you find out.
Right, yeah.
I think Andres has his hand up. You wanna go?
Sorry, yeah.
Yeah, go ahead.
I don't know who. I think several people have questions. Okay, I have one very general question and then a couple of specific. But the very general is there is this kind of a long dream of doing forcing for arithmetic as opposed to doing forcing for set theory. You said a few things in the beginning of your lecture today. Do you think this is somehow Schellach's kind of hidden agenda to try to build forcing for arithmetic, and he's kind of testing the waters, so to speak, by building this fulfillment notion, and maybe he didn't really have much follow-up, as you said, except for very few additional works. And but do you think this might be construed as a mild step on the road to forcing for arithmetic? Do you think this?
I mean, to be honest, that's what I've thought about this a lot. I love this question. I wish I could say yes, but I've thought about it, and I think the answer is no. And I actually think that Schellach, he has this paper called Logical Dreams or something, where he kind of says something similar, and the answer is no, because, and this kind of gets at actually what I think is, I mean, obviously I stand by what I presented here. I think it's great. I think it's really interesting, but it's not, I think, the right way to approach independence in PA, and I actually don't think we have the right way. And the reason why forcing is the right way to do independence in ZF is that you get equiconsistency results. And what we're doing here, I mean, what I did here and what every proof of independence in PA that I know of any kind does, with the exception of the really pathological ones, like the liar thing, is you argue in ZFC that something is true in the standard model. And then you show that from PA plus that sentence, you can prove COM-PA. So you don't get equiconsistency results. You're not, it's not this general model theoretic thing where you take a model, you build another one, blah, 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 blah. So there's something missing with regards to that. I mean, someone can correct me if I'm wrong, but I think that we don't have an example of a sentence that everyone kind of agrees is very mathematical, so that it and its negation are equiconsistent over PA, and it's independent. And that's what makes forcing, I think, kind of special. So I think maybe he was testing the waters. Definitely there is some forcing like themes where you're building something and it's approximating something else. Wilkie kind of implies this. He wrote a paper about this, and he uses, instead of the model star, he uses the forcing relation, and he calls them approximating structures. But as far as I mean, I thought a lot about this. I don't think it's quite right. But I wish it was, honestly, because yeah.
This sort of, the reason why you get the equiconsistency result results in forcing for ZF, in a way, maybe connected to the fact that you have a truth lemma and a definability lemma, the fact that you have this sort of a kind of very strong asymmetry. On the one hand, you build the forcing, the star forcing, syntactic forcing relation, yet you have all these generic models and you have all these, all those kind of external way to test that gives you the dual thing. Whereas here, it seems that you only have the syntactic version. There is no, so to speak, like a generic model theorem or a forcing theorem, so to speak, for this, or fulfillment theorems. Maybe you might want to put. And so what might be missing to get such a thing?
Yeah, right. I think you're totally right. And this is, of course, what makes forcing so amazing. You'd only have syntactic forcing here because as arithmetics, you only have syntax, right? And that's the barrier that I don't see how to get over it, and I don't think that anyone has, which is why we're in this kind of impasse. Yeah, I mean, the forcing, because you have the syntax semantics thing going on at the same time, it's what makes it go, and that's what's missing here is semantics.
Right. Okay. Yeah. Maybe somebody else. Another question.
I have a question and just a quick historical remark, but I don't want to be cutting in line. Is that okay?
It's okay with me.
Yes, David was next.
Okay.
Go ahead.
So my question, I'll make it quick. The Pi01 statements that you discussed today, they imply ConPA, but are they equivalent to ConPA?
I don't know. I think not. I'd have to check, but my guess is no, because the Pi01 statement implies the Pi021, which looks very similar to Paris-Harrington, which is much stronger than ConPA. And I would be willing to bet that they're more likely to be equivalent to Paris-Harrington than ConPA, but I don't know off the top of my head.
Okay, thank you.
Yeah, it's actually a good question. I should think about that. Yeah, thank you.
And yes, I didn't realize that they imply the Pi2 version, so that's interesting. The historical comment, just to make it quickly, one, you mentioned Paris-Harrington and the order of the names. As I recall, and I hope others will correct me, Paris had a protoform version of this theorem, which wasn't in terms of partition relations, but in terms of indicators. And as I recall, Harrington simplified that. So I think the ordering has to do with acknowledging Paris's initial work.
Okay, that's interesting. That's good to know.
Yeah. Work on indicators is notably in Kirby's thesis.
Oh, absolutely. Yeah, that's right. So it should be Kirby, Paris.
And then Paris had a version that predated the Paris-Harrington version, which was combinatorial. Had the notion of dense sets. A set with one dense.
That's right.
Every partition of triples had a homogeneous. It's n plus one dense if there's an n dense homogeneous set for partitions of type of Hans triples.
Okay, that's very interesting. Thank you.
And if that function's total, then you could build a model of Peano arithmetic.
Okay. Yes, my knowledge of the history of this is very much lacking, so this is very helpful. Thank you.
Yeah.
I was there. I don't think I'm hard done by. I certainly did. I was involved in some of the groundwork, but they were out of my league and doing that stuff. Regarding the order of the names, Paris had written to explaining his n density result, and I remember Jeff said one morning, he said, I got this letter from Harrington, and in those days you corresponded by handwriting letters, and giving this improvement. And the handbook on mathematical logic was in its, I don't know, its proofs or something, but John Barwise was the editor, and he really wanted this article to be the last article in it, so it was rushed into print, and I think Harrington basically wrote it, and he insisted on putting Paris's name first, because he was a gentleman or whatever.
Oh, that's good to know. Yeah, because I noticed that literally every single paper had it like this, and I thought it was kind of strange. But that's fascinating. Yeah, I mean, in their paper, they thank Barwise for quote something like encouraging us, forcing us to write it, and basically writing it himself when we didn't, something like this. But yeah.
But I also have a question.
Yes.
Your pi1 statement, and I guess Sheila's too, they're come somehow very close to these pi2 statements, and as you said, the shorthand version of the pi2 statements is the function grows too fast.
Mm-hmm.
And you got rid of that, but I kind of have a feeling, is it hiding somewhere, that fast growth, or where has that problem gone that I'm not getting a feeling for what makes these particular things jump the barrier to not being improvable.
Yeah, so you're totally right, and this is true exactly in Sheila's as well. I mean, my idea here is similar to his idea in his paper. Because what you do is you have this pi01 sentence, and you argue in PA that it's equivalent to a pi02 sentence, where you drop the primitive recursive bound. And this is because of this F collapse, that you're controlling the colorings on some small subset. And then when you actually prove the independence result, you just use the pi02 one, and the same fast growing function stuff appears. And at one point I sat down and I thought, well, could I just skip this and prove the theorem just using the pi01 one? And it was not clear to me how to prove it directly. I mean, there's a cut that if you want to put it in proof theoretic terms, there's a cut that I don't know how to eliminate in the natural deduction. And that's true for Sheila's theorem as well. There's something funny going on there about that. I don't disagree with you. I don't know exactly where the fast growing function goes though. I don't know if that answers your question or not. You still look skeptical, which I would be. I mean, I am, but I don't know.
Thank you. That's good.
I have a question.
Yeah.
In your paper and share paper, the formula was in Pendence's normal form, isn't it?
Sorry, say that again.
The formulas in the share paper and your paper was in Pendence's normal form.
Oh, the formula, yeah. So right, in pre-next normal form, yeah. So that was in the draft that's on the archive. I don't actually know if you need it. I certainly, here I tried to simplify the presentation, and I think I swept some details under the rug, but I don't know if it totally matters. What's your question about it?
In the presentation, you don't use it. It does affect any proof theorem?
I don't think it does, because I mean because the syntactic nature. I mean, syntax matters in how you define these fulfillment conditions to a point, right? So if things aren't in pre-next normal form, maybe you need n to be a little longer in order to make sense of the sentence or whatever. But I mean, in the long run, I don't think it affects the truth of the theorems or anything like that. That makes sense.
Okay. And okay.
Does that answer your question?
All right. Look, I guess we should thank Corey again. That an excellent talk, and
thank you.
And good to see you. And I just want to tell you that next week Ali will talk about something close to model theory of PA and set theory as well. So but it will be at 7 p.m. our time.